In an exploration of the cosmos that stretches back to the earliest moments of existence, researchers stand before the enigma of the universe's birth, tracing the origins to an event known as the Big Bang. Approximately 13.8 billion years ago, an event of incomprehensible magnitude marked the beginning of everything. From a state of extreme heat and density, referred to as a singularity, the universe underwent a period of rapid expansion and cooling that set the stage for all subsequent cosmic phenomena. As the universe expanded, it cooled sufficiently for subatomic particles and atoms to form, creating the building blocks for the first stars and galaxies. This pivotal era in cosmic history is not merely a theoretical construct, but is evidenced by the cosmic microwave background radiation, a pervasive glow that is the afterglow of the universe's formation, still observable today. The cosmic journey of the universe proceeded through distinct stages. The initial burst of expansion, known as inflation, smoothed out irregularities and laid the groundwork for a uniform cosmos. Following this, during a period called nucleosynthesis, protons and neutrons came together to form the nuclei of atoms. The photon decoupling phase, occurring 380,000 years after the Big Bang, allowed for the release of photons as electrons and protons combined, which we now observe as the cosmic microwave background radiation. Subsequent to these formative stages, the universe entered an era of star and galaxy formation approximately 1 billion years after the inception. Matter, influenced by gravity, began to clump together, igniting the nuclear furnaces of the first stars and assembling the earliest galaxies. Over the next several billion years, these galaxies congregated to form the vast cosmic web that characterizes the structure of the universe on the grandest scales. The Big Bang theory is cemented by a robust body of evidence. Beyond the cosmic microwave background radiation, the abundance of light elements such as hydrogen and helium align with predictions from the theory. The architecture of the universe and the redshift observed in light from distant galaxies, indicating their recession from us, further substantiate the concept of an expanding cosmos that originated from a singular event. Yet, the narrative of the universe's evolution is far from complete. Mysteries persist, such as the nature of dark matter and dark energy, which together comprise the majority of the universe's content, yet defy direct detection. The inflationary theory, detailing the universe's exponential expansion in its first fleeting moments, remains a fertile ground for investigation. Questions about the matter-antimatter asymmetry challenge scientists, as does the quest to understand the properties of the early universe. Remarkably, the cosmos continues to yield new insights. Astronomers utilizing cutting-edge technology, such as the James Webb Space Telescope, peer deep into the past, observing galaxies from the time when the universe was a fraction of its current age. These observations promise to refine understanding of how the earliest stars and galaxies formed and evolved. The Big Bang theory, while robust and widely accepted, is a living scientific paradigm, evolving with each new discovery. The quest for understanding presses on, with researchers probing the depths of space and time to unravel the mysteries of the universe's origin and evolution. It is a journey that transcends the boundaries of human experience, reaching back to the dawn of everything, and it is a journey that is far from over. In the enigmatic expanse of the cosmos, black holes stand as one of the most captivating and enigmatic phenomena. These massive entities exert a gravitational pull so intense that even light cannot escape, rendering them invisible and mysterious to the observer. Traditionally, black holes are understood to emerge from the gravitational collapse of massive stars, a process that occurs when the internal pressure generated by nuclear reactions can no longer withstand the force of gravity. Yet the universe is a vast playground of theoretical possibilities, and one of the more exotic conjectures has been the idea of a black hole formed not from star stuff, but from light itself. Termed Kugelblitze, a German term akin to ball lightning, these theoretical black holes were thought to manifest from the concentration of vast amounts of electromagnetic radiation. According to Einstein's theory of general relativity, it is energy that bends the fabric of space-time, creating the well of gravity that can lead to a black hole. Thus, in principle, if enough light, carrying energy but no mass, could be focused into a sufficiently compact space, a black hole could form. However, new research has cast doubt on the existence of such Kugelblitze. The study, awaiting publication in the prestigious journal Physical Review Letters, approaches the issue by considering quantum effects, which general relativity does not account for. Specifically, the research examines the Schwinger effect, a quantum phenomenon where intense electromagnetic energy is converted into matter in the form of electron-positron pairs. This process, also known as vacuum polarization, effectively drains energy from the electromagnetic field that would otherwise contribute to the formation of a Kugelblitz. Through rigorous calculations, the researchers determined that the rate at which energy would be siphoned away by the Schwinger effect outpaces the rate at which electromagnetic field energy could accumulate. Consequently, even under extraordinarily extreme conditions, electromagnetic radiation alone could not achieve the necessary energy density to spawn a black hole. This revelation holds significant weight, as it implies that not only are Kugelblitze impossible to produce in laboratory settings, but also that they're unlikely to form naturally within the universe. The implications of this finding extend beyond the refutation of a theoretical black hole. It places notable constraints on cosmological models that have considered the existence of Kugelblitze. Furthermore, it underscores the importance of integrating quantum mechanics with general relativity, a pivotal step in advancing the understanding of the universe's most profound and complex mysteries. The aspiration to reconcile the quantum realm with gravitational theory remains a monumental task in physics. Yet, the outcome of this study provides a beacon of progress, demonstrating that quantum effects can indeed be harmonized with gravitational phenomena to yield definitive scientific insights. This harmonization is not merely theoretical. It has tangible implications for the study of astrophysical objects and the fundamental laws that govern them. Encouraged by these findings, the research team is poised to further investigate the role of quantum phenomena in various gravitational contexts. Such explorations are not only of academic interest, but also bear practical significance, potentially guiding future technological applications and fostering a deeper comprehension of the universe's inner workings. In the vast expanse of the cosmos, modern cosmology is at the forefront of unraveling some of the universe's most profound mysteries. This scientific field, focused on the grandest scales, probes deep into the enigmas of dark matter and dark energy, which together form the backbone of the cosmic web. Dark matter, an invisible substance, makes up a significant portion of the universe's total mass, but does not emit, absorb, or reflect light, making it extremely difficult to detect directly. It is known primarily through its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. Meanwhile, dark energy, even more mysterious, acts as a sort of anti-gravity, driving the accelerated expansion of the universe and dominating its current energy content. The cosmic microwave background radiation, another pivotal element in cosmology, offers a snapshot of the infant universe just hundreds of thousands of years after the Big Bang. This residual glow, detected in all directions, provides critical clues about the early stages of the universe's expansion and its initial conditions. As cosmologists continue to push the boundaries of technology and observation, they aim to untangle the complexities of galaxy formation and the precise rate of the universe's expansion. These efforts are crucial in piecing together the puzzle of our universe from its moment of inception to its ultimate fate. Understanding these cosmic phenomena not only expands human knowledge of where the universe came from, but also where it is heading. The journey through the cosmos continues to inspire and challenge as it stretches the limits of what is knowable, guiding humanity ever closer to the elusive cosmic dawn. As the James Webb Space Telescope celebrates its second anniversary, it marks this milestone with a stunning visual achievement, capturing the intricate interaction between two galaxies known as ARP-142. This celestial pair, individually cataloged as Penguin, NGC 2936, and Egg, NGC 2937, presents a vivid tableau of cosmic evolution and interaction. In the new images from the James Webb Space Telescope, the galaxies are seen in the throes of a slow, graceful dance that is set to culminate in a merger millions of years from now. This interaction began between 25 million to 75 million years ago, highlighting the prolonged and dynamic processes that characterize galactic evolution. The telescope's infrared capabilities allow it to observe a blue haze of stars and gas enveloping the two galaxies, a testament to the ongoing gravitational forces at play. The images reveal the transformation of the Penguin from a spiral galaxy to its current state, where features such as a beak, head, backbone, and a fanned-out tail are discernible, thanks to the gravitational interactions that have sculpted its structure. This galaxy, still abundant in stars and dust, showcases areas where new star formation is actively occurring, highlighted by regions of gas and dust crashing together under gravitational forces. Surrounding these nascent stars is a smoke-like expanse filled with carbon-containing molecules, which are vividly detected by Webb's advanced instrumentation. On the other hand, the egg maintains its elliptical form, dominated by older stars and exhibiting less gas and dust, which limits new star formation. This stability in its structure, despite the nearby gravitational dance, is attributed to the similar mass of the two galaxies, preventing the egg from being significantly distorted or consumed by the Penguin. This observation not only offers a glimpse into the physical changes induced by galactic interactions, but also underscores the role of advanced telescopes like James Webb in enhancing understanding of the universe. The technology aboard the James Webb Space Telescope, an international collaboration involving NASA, the European Space Agency, and the Canadian Space Agency, allows for unprecedented views of the universe, from galaxy mergers like ARP-142 to deeper explorations into the origins of stars and planetary systems. These insights are crucial for unraveling the mysteries of galaxy formation and evolution, providing a clearer picture of the dynamic processes that shape the cosmos. As this telescope continues to peer into the depths of space, it brings humanity closer to comprehending the vast, intricate tapestry of the universe. This ongoing mission not only expands scientific horizons, but also continues to capture the collective imagination with its revelations of the cosmos' awe-inspiring beauty and complexity. Transitioning from the broader implications of the James Webb Space Telescope's imagery, a closer examination of the individual images of ARP-142 reveals a striking contrast in the portrayal of these merging galaxies when viewed through different astronomical instruments. The detailed visible light image captured by the Hubble Space Telescope and the Webb's near-infrared image illuminate distinct yet complementary aspects of these celestial bodies. In the visible light spectrum captured by Hubble, the Penguin Galaxy, NGC 2936, is depicted with vivid clarity. Its features are dramatically highlighted, with a bright blue beak and a body gracefully arched by an arc of bright brown dust. This dust traces the galaxy's dynamic past and ongoing transformation, shaped by the gravitational forces exerted by its dance with the egg galaxy. Switching to the near-infrared spectrum with the James Webb Space Telescope, the appearance of the Penguin shifts remarkably. The same regions, now observed in infrared, display varying shades of pink across the beak, head, and back, while its tail-like region diffuses into a blend of lighter pinks and blues. This shift in coloration and detail is due to Webb's ability to peer through clouds of dust that obscure certain features in visible light, revealing the underlying structures and new star formation areas not previously seen. The egg galaxy, NGC 2937, presents a different set of contrasts. In Hubble's observations, it shines in a bright, gleaming yellowish-white hue, its smooth elliptical shape stark against the backdrop of space. However, through the lens of Webb, the egg is enveloped in layers of blue, appearing slightly enlarged. This transformation in visibility is attributed to Webb's adeptness at capturing the cooler material of the galaxy, which does not glow as brightly in visible light, but is radiant in infrared. These comparative images not only highlight the differences in technology and observational capabilities of the Hubble and James Webb telescopes, but also underscore the multifaceted nature of galaxies. Each set of wavelengths unveils different characteristics of the same objects, providing astronomers and scientists with richer, more detailed information to piece together the life cycles of galaxies, their interactions, and the broader mechanics of the cosmos. Such detailed imagery is essential in advancing the understanding of how galaxies merge and evolve, offering a clearer view of the universe's complex and dynamic architecture. Building upon the detailed observations provided by both the Hubble and James Webb Space Telescopes, the scientific insights gleaned from the study of ARP 142 extend far beyond mere visual documentation. The interaction between the galaxies known as the penguin and the egg is a dynamic demonstration of the processes that drive galactic evolution and transformation. As these two galaxies continue their slow cosmic dance, drawn inexorably together by gravitational forces, they are on a trajectory to eventually merge into a single entity. This monumental event, projected to occur over the next few million years, is not merely a collision, but a fusion that will give birth to new celestial formations. The gravitational interactions at play not only influence the shapes and structures of the galaxies, but also trigger crucial processes such as star formation. In regions where the gravitational forces are most intense, clouds of gas and dust within the galaxies experience compression. This compression raises the density of these clouds to a critical threshold, initiating nuclear fusion, the fundamental process that births new stars. Observations of ARP 142 have shown areas of active star formation, particularly in zones where gravitational interactions are most disruptive. These insights underscore the role of galactic interactions in creating the nurseries of new stars, contributing significantly to the evolutionary narrative of the universe. The advanced technology onboard the James Webb Space Telescope enhances the understanding of these phenomena. Equipped to observe in the near-infrared spectrum, Webb can see through clouds of dust that typically obscure the view in visible light. This capability allows astronomers to observe the core regions of galactic interactions, unveiling where and how new stars are forming. Thus, Webb's observations are not merely about capturing images, but about deepening the understanding of cosmic processes that govern galaxy formation and evolution. Moreover, these observations have broader implications for the comprehension of the universe and the future of space exploration. By studying galaxy mergers like ARP 142, scientists can refine theoretical models of galaxy formation and evolution. These models are crucial for predicting how galaxies will grow and change over billions of years, providing insights into the past and future of the universe itself. Additionally, the data gathered by telescopes like Webb aids in preparing for future missions that may venture further into space. Understanding the complex dynamics of galaxy mergers and star formation equips scientists with the knowledge necessary to navigate and study the universe more effectively. In essence, every image and data point captured brings humanity one step closer to answering profound questions about the cosmos' origin, structure, and ultimate fate. In conclusion, the ongoing study of ARP 142 not only enlightens current scientific knowledge, but also paves the way for future explorations, ensuring that the journey into the depths of space continues to illuminate the mysteries of the vast universe surrounding us. In the bustling city of Berlin, a recent development has captured the attention of those yearning to understand the cosmos. Astronomer Sebastian Ziebe, armed with the formidable James Webb Space Telescope, is at the frontier of a quest that could redefine humanity's place in the universe: the search for extraterrestrial life through the study of exoplanet atmospheres. Ziebe's expertise is trained on small rocky exoplanets, the kind that may host atmospheres conducive to life. While these celestial bodies lie light years away, his meticulous scrutiny is bridging the vast distances. Graduating with honors on June 25th, Ziebe's ambition is fueled by a simple yet profound objective: to find traces of life. The Max Planck Institute for Astronomy and Leiden Observatory, with which he is affiliated, provide a fertile ground for his pioneering research. Ziebe's methodology includes the analysis of temperature variations on exoplanets to infer the presence of an atmosphere. One such object of study is K2-141b, a mesmerizing world where one hemisphere eternally basks in the scorching embrace of its star, while the other endures a frigid existence. The disparity is so stark that it causes rock itself to transition into vapor, potentially giving rise to an atmosphere composed of this rock vapor. A promising lead in Ziebe's work is the detection of heat transfer across the planet, which could hint at atmospheric conditions tempering the otherwise extreme climate. This ongoing investigation, with future data anticipated from the James Webb Space Telescope, is expected to shed more light on the enigmatic conditions of these distant worlds. ZEBA also scrutinizes emission spectra for signs of specific molecules like carbon dioxide, a prevalent marker of planetary activity. His gaze turned to TRAPPIST-1c, an exoplanet sharing similarities with Venus, prompting speculation about a comparable atmosphere. However, the search for CO2 came up short, suggesting that TRAPPIST-1c may be devoid of a significant atmosphere, a stark contrast to Venus' dense CO2 shroud. The researchers' journey began with the infrared gaze of the Spitzer telescope, later transitioning to the advanced capabilities of the JWST during his PhD. With humor, he expresses a wish to multiply these tools, envisioning a fleet of telescopes to probe the heavens with unprecedented clarity. ZEBA looks ahead to the possibilities enabled by future instruments, such as the extremely large telescope in Chile, the Habitable Worlds Observatory, and the Life space mission, which promise to extend the reach of his investigations. The absence of detected atmospheres in some instances does not deter ZEBA, rather it sharpens the scientific process. Each observation, regardless of outcome, enriches the collective understanding and refines techniques for the next foray into the unknown. It is through this relentless pursuit, marked by both its triumphs and its seemingly quiet moments, that the pathway to discovery is paved. The pursuit of knowledge is relentless, and as one journey concludes, another beckons. The narrative of exoplanetary research is a testament to the human spirit's insatiable curiosity, and the quest continues, ever driven by the profound questions that propel explorers like ZEBA to look upward and beyond. The search for life, for worlds beyond our own, is a chronicle of both the seen and unseen, a story etched in the light of distant stars and the shadows of the planets that dance around them. The Breakthrough Discuss 2024 conference, hosted at the prestigious University of Oxford, marks a pivotal gathering under the theme A Cosmic Tapestry for Exploration, weaving novel strands in artificial intelligence, astrobiology, and space missions. Scheduled for July 18 to 19, this assembly is set to explore the increasingly intertwined disciplines of AI, astrobiology, and space missions, focusing on their collective role in the quest for extraterrestrial life. This conference, organized by Breakthrough Initiatives, founded by Yuri Milner and his wife Julia in 2015, continues to attract the intellectual prowess of global experts, including renowned figures such as the late Stephen Hawking and entrepreneur Mark Zuckerberg. The event has rapidly evolved into a cornerstone for scholarly discourse on space exploration, pulling in a stellar array of scientists, engineers, and visionaries from institutions like NASA, the SETI Institute, and the European Space Agency. The theme for this year's conference not only highlights the integration of cutting-edge technologies, but also underscores the growing synergy between different scientific fields, aiming to push the boundaries of current methodologies in the search for life beyond Earth. The agenda is structured around three main strands: science transformed by artificial intelligence, fabric of life on and off the Earth, and new frontiers in space exploration. Artificial intelligence stands at the forefront of the first strand, with discussions led by experts such as Alexis Boukouvalis of DeepMind and Regu Angappan from Sandbox AQ. They, alongside other prominent researchers from Harvard University and the SETI Institute, will provide insights into how AI is reshaping the ways astronomical data is interpreted, particularly in detecting and analyzing exoplanets and technosignatures. The second strand delves into the realm of astrobiology, chaired by Penny Boston and Chris Glein, featuring cutting-edge research on the potential habitats for life within our solar system, including the icy moons such as Europa and Enceladus. This segment will also cover the latest theories in the geochemistry of potentially habitable worlds and the ongoing search for biosignatures in exoplanet atmospheres. Advancements in space technology form the crux of the third strand, new frontiers in space exploration, with discussions on innovative propulsion systems and the design of miniaturized spacecraft aimed at enhancing our exploratory capabilities, as well as updates on ambitious missions like NASA's Europa Clipper and the ESA's ExoMars rover. In addition to these focused discussions, the conference will feature highlight talks from luminaries such as Arpita Roy of Schmidt Sciences and Alison Lowndes from NVIDIA, providing broader perspectives on the socio-philosophical implications of discovering life beyond Earth and the role of industrial and philanthropic efforts in advancing space sciences. Concluding with a dynamic panel discussion, the Breakthrough Discuss 2024 conference aims to foster interdisciplinary dialogue and seed new collaborations that could not only redefine humanity's search for extraterrestrial life, but also enhance the collective understanding of the cosmos and humanity's place within it. This convergence of AI, astrobiology, and space mission technologies at the conference underscores a transformative era in space exploration, promising new discoveries and innovations in the years to come. Building on the interdisciplinary momentum set by the conference introduction, the first segment zeroes in on the revolutionary role of artificial intelligence in space exploration. Keynote speakers from leading tech entities such as DeepMind and SandboxAQ take the stage to shed light on AI's transformative impact in the astronomical sphere, particularly in the analysis of vast datasets and the identification of technosignatures. The potential of AI in this field is vast. It extends beyond mere data analysis to fundamentally altering the methodologies used in the search for extraterrestrial life. Through sophisticated algorithms and machine learning techniques, AI is enabling researchers to sift through the noise of cosmic data to pinpoint potential signs of otherworldly life. This includes analyzing light patterns from distant stars to detect possible exoplanets and examining atmospheric compositions to identify possible biosignatures. Moreover, the application of AI is not limited to data interpretation. It is also playing a crucial role in enhancing the capabilities of space missions through the automation of spacecraft operations and the optimization of flight paths. This dual application not only increases the efficiency of missions, but also reduces the risk and cost associated with human error. The discourse provided by experts from DeepMind and BoxAQ goes on to highlight specific case studies where AI algorithms have led to significant breakthroughs in detecting exoplanets and other celestial phenomena. This not only serves as a testament to AI's potential in this field, but also underscores the importance of continued investment and research in AI technologies tailored for space exploration. This segment of the conference, rich with expert insights and real-world examples, paints a promising picture of AI's role in the future of space exploration. It demonstrates how AI is not just a tool, but a potential game-changer in the quest to understand the cosmos and possibly discover signs of life beyond Earth. This exploration of AI's capabilities sets the perfect precursor to discussions on the astrobiological aspects of the search for life, seamlessly transitioning into the next segment focused on astrobiology and the search for biosignatures. Transitioning from the technological advancements facilitated by AI in space exploration, the conference delves into the core of astrobiology with a focus on the search for biosignatures. This segment brings to the forefront experts from NASA Goddard Space Flight Center, among other distinguished research institutions, who share their latest findings and theories on the potential habitats that could harbor life beyond Earth. Central to the discussions is the intricate geochemistry of worlds that lie within and outside our solar system, considered potentially habitable. Experts present detailed analyses of the chemical compositions and environmental conditions of planets and moons, which could suggest the presence of biological activity. Emphasis is placed on the unique and extreme environments like the subsurface oceans of icy moons, such as Europa and Enceladus, which are thought to possibly support microbial life beneath their icy crusts. The significance of biosignatures is thoroughly examined in this segment. Biosignatures are any substances, such as elements, molecules, or phenomena, that provide scientific evidence of past or present life. Speakers discuss the technologies and methodologies used to detect these signatures, from spectroscopy used to analyze atmospheres to the robotic explorers that might one day drill through miles of ice to sample hidden oceans. This segment not only highlights the current technological and methodological approaches to detecting biosignatures, but also discusses the implications of these findings. The discovery of biosignatures would not only prove that Earth is not unique in hosting life, but also fundamentally shift the scientific understanding of life itself. Furthermore, the presentations explore the collaborative nature of space exploration missions that aim to find biosignatures. These missions exemplify the intersection of various scientific disciplines, including geology, chemistry, and biology, all converging to answer the profound question of whether humanity is alone in the universe. The discussions on biosignatures and their implications for astrobiology set a comprehensive backdrop for the upcoming segment focused on new frontiers in space exploration. This ensures a seamless transition into exploring how upcoming and future missions are designed, not just to reach farther into space, but to bring back data that could confirm the existence of life beyond Earth. Nestled within the vast expanse of the Milky Way galaxy lies the Solar System, a cosmic enclave that resides in the Orion Cygnus arm. This sector of the galaxy houses an intricate system of celestial bodies that are bound together by the gravitational force of the Sun, a medium-sized star that accounts for over 99% of the system's total mass. At the heart of the Solar System is the Sun, a luminous sphere whose gravitational pull orchestrates the movements of an array of orbiting objects. These include the 8 major planets, a diverse group of dwarf planets such as Pluto, numerous moons, and a multitude of smaller bodies like asteroids and comets. The solar system's planets are categorized into 2 distinct groups based on their composition and location relative to the Sun. The 4 inner planets, Mercury, Venus, Earth, and Mars, are terrestrial, primarily composed of rock and metal. These are followed by the 4 giant planets, Jupiter, Saturn, Uranus, and Neptune, which are significantly larger and possess thick atmospheres, mostly of hydrogen and helium. Jupiter and Saturn are known as gas giants, while Uranus and Neptune are often referred to as ice giants due to their higher concentrations of ices such as water, ammonia, and methane in their composition. Pluto, once considered the 9th planet, resides in a region known as the Kuiper Belt, a vast, donut-shaped ring of icy bodies beyond Neptune where thousands of small, frozen objects orbit the Sun. The reclassification of Pluto to a dwarf planet in 2006 by the International Astronomical Union reflects the evolving understanding of the solar system's dynamic nature. In addition to the planets and Pluto, the solar system is home to the asteroid belt, a crowded zone located between Mars and Jupiter. This belt contains numerous irregular-shaped bodies that are remnants from the solar system's early formation days. Further from the Sun, the Kuiper Belt and the distant Oort cloud are reservoirs for comets, providing a source for those that occasionally visit the inner solar system. The diversity of the solar system extends to the many moons orbiting the planets, each with unique geological histories and characteristics. For instance, Jupiter's moon Europa and Saturn's moon Enceladus are covered in ice and are prominent candidates in the search for extraterrestrial life due to the potential subsurface oceans beneath their frozen exteriors. This broad assembly of sun, planets, moons, and smaller bodies are not only a focus of scientific study, but also a testament to the complexity and beauty of the universe. As humanity reaches further into space with probes and telescopes, the knowledge of our immediate cosmic neighborhood continues to expand, revealing the intricate dance of celestial mechanics and the rich tapestry of the solar system's components. The prevailing theory on the formation of the solar system centers around the concept of the solar nebula, a primordial, rotating cloud composed of gas and dust. This nebula is believed to have collapsed under its own gravitational pull, leading to the formation of the Sun at its core. The process generated immense heat and a spinning disk of material that gradually coalesced into the planets, moons, and other bodies that orbit the Sun today. As the nascent Sun ignited, its solar wind swept away much of the lighter elements from the inner part of the solar system, leaving behind mostly rocky materials to form the terrestrial planets. Farther from the Sun, where temperatures were cooler, icy compounds and gases could remain solid, contributing to the formation of the giant gas and ice planets with their complex ring systems and numerous moons. Over billions of years, the solar system has undergone dynamic processes that continuously shape its celestial bodies. Gravitational forces, especially from the larger planets like Jupiter and Saturn, have had profound effects on the solar system's architecture. These forces can alter the orbits of smaller bodies, leading to occasional collisions and accretions that have left impact craters on many planetary surfaces. The Moon, as observed from Earth, showcases a record of such impacts with its numerous craters. Meteorites, remnants of asteroids, or cometary material that survive passage through Earth's atmosphere and impact the surface provide valuable clues about the early solar system's conditions. These space rocks have been extensively studied to understand the distribution of elements and isotopes that were present during the solar system's formation. Comets, often described as dirty snowballs of ice and dust, originate from the distant reaches of the solar system. When their elongated orbits bring them closer to the sun, the heat vaporizes their ices, releasing gas and dust that form spectacular glowing comas and tails. The interaction of cometary material with planetary atmospheres and surfaces has played a crucial role in delivering water and organic compounds, which are essential for life as known on Earth. The continuous study of these processes not only provides insights into the history and evolution of the solar system, but also enhances the understanding of planetary systems around other stars. By examining the forces and events that have sculpted our own solar system, scientists can better comprehend the potential habitability and development of distant exoplanetary systems. As exploration extends further into the cosmos, the lessons learned from the solar system's formation and evolution remain fundamental in the quest to understand the universe's broader mysteries. The quest to discover life beyond Earth has led scientists to examine not only distant exoplanets, but also the more accessible moons and planets within our own solar system. Two of the most promising candidates for harboring life are the moons Europa and Enceladus. Orbiting Jupiter and Saturn respectively, these moons are covered in thick ice shells which, scientists believe, conceal vast oceans beneath their frigid surfaces. The potential for these subsurface oceans to support microbial life forms draws a fascinating parallel to hydrothermal vents on Earth's ocean floors, where life thrives without sunlight, deriving energy instead from the heat and minerals emitted by underwater volcanic activity. Europa's icy surface is crisscrossed with reddish-brown streaks, suggesting the presence of salts and organic compounds that may have seeped up from the ocean below through cracks in the ice. Similarly, Enceladus emits impressive plumes of water vapor and ice from its south polar region, indicative of geologic activity beneath its surface. These plumes have been found to contain organic molecules, further fueling speculation about the possibility of life. Beyond the icy moons, Mars has long been a focus of astrobiological research due to its relatively hospitable environment in the distant past. Geological evidence, including the presence of dried riverbeds and minerals that form in the presence of water, suggests that Mars once had liquid water on its surface, a key ingredient for life. Moreover, recent missions have detected fluctuating methane levels in the Martian atmosphere, a phenomenon on Earth that is largely attributed to biological activity. While abiotic processes could also be responsible, this discovery adds another layer of intrigue to the potential for life on Mars. Numerous missions have been designed specifically to explore these possibilities. For Europa, the upcoming Europa Clipper mission by NASA aims to conduct detailed reconnaissance of Europa's ice shell and the ocean it may hold beneath. Similarly, the Enceladus Life Finder mission is proposed to fly through Enceladus plumes to capture and analyze the ejected material for signs of life. Mars, on the other hand, has been the target of multiple rovers and orbiters from various space agencies, each equipped with sophisticated instruments to further investigate the planet's geological history and current conditions. These scientific endeavors not only aim to answer the age-old question of whether Earth is unique in hosting life, but also to expand the understanding of the conditions under which life can emerge and thrive. As these missions collect and send back data, they pave the way for future explorations and perhaps even human missions to these distant worlds, opening new frontiers in the search for extraterrestrial life. In an era marked by technological leaps, SpaceX stands at the forefront with its audacious Mars colonization program, a vision cast by none other than Elon Musk. The program's inception can be traced back to Musk's early fascination with Mars, notably highlighted during his participation at the 2006 Mars Society Conference. Before laying the foundations of SpaceX in 2001, Musk had already embraced the notion of Martian missions and had briefly served on the Mars Society's board of directors. SpaceX's Mars program, colloquially known among enthusiasts as Occupy Mars, aims to establish a self-sustained, large-scale settlement on Mars. Musk envisions this endeavor as a crucial step towards ensuring the long-term survival and well-being of humanity. Such a bold initiative pivots on the development and deployment of the Starship, a groundbreaking, fully reusable super heavy-lift launch vehicle. Dubbed the Holy Grail of rocketry, Starship represents a paradigm shift due to its reusability and potential for extraplanetary colonization. The colonization plan has stirred a mixture of excitement and skepticism. While many laud the pioneering spirit of further human involvement beyond Earth, others question the existential rationale, practical execution, and legal implications of establishing a human foothold on Mars. Musk's engagement with Martian advocacy dates back to at least 2001, with public declarations of his Martian ambitions surfacing around 2007. Over the years, SpaceX has articulated its vision of Martian colonization as a strategy for human species preservation. The company has proposed various concepts over the decades, initially considering space tugs and later the ambitious Red Dragon missions, which were eventually shelved in favor of the more capable Starship. The cornerstone of SpaceX's strategy involves the establishment of Starbase and the Star Factory in Boca Chica, Texas. These facilities are dedicated to the construction and launch of the Starship, which promises to drastically reduce space travel costs through its reusability. The Starship, comprising a super heavy booster and a second-stage spacecraft, is powered by Raptor engines designed for high-pressure conditions and minimal soot production, essential for the sustainability of long-duration space missions. Indeed, the first missions to Mars will focus on cargo, delivering the necessary infrastructure for future human settlers. These missions will transport machines to produce vital resources like fertilizer, methane, and oxygen from Martian raw materials. Transparent domes for crop growth and habitats will also be established to support the initial human occupants, who will number around 12 in the early missions. Their primary tasks will include setting up the propellant plant and power systems for what will eventually become Mars Base Alpha. As infrastructure solidifies and launch costs decrease, the plan is to ramp up the number of settlers transported to Mars, aiming for a self-sustaining colony that could burgeon into a thriving community, involving numerous economic actors beyond SpaceX. This vision extends towards transforming Mars into a free planet, a concept that has already begun to permeate public and legal discourse through initiatives like the Starlink Terms of Service. SpaceX's Mars colonization program is not just a testament to human ingenuity and ambition, but also a contentious topic that invites rigorous debate over the feasibility, ethics, and future of human space exploration. As the program unfolds, it continues to captivate and challenge the global community, reflecting humanity's unyielding quest to reach beyond the known limits. The linchpin of SpaceX's Martian ambitions, the Starship, represents a revolutionary stride in space technology, primarily due to its full reusability. This super heavy-lift launch vehicle is pivotal for reducing the cost of space travel, a fundamental aspect of making Mars colonization feasible. The development of the Starship is a testament to SpaceX's commitment to innovation and its relentless pursuit of redefining what is possible in aerospace technology. Constructed from stainless steel, the Starship is both robust and relatively inexpensive compared to materials like carbon fiber. This choice not only aids in withstanding the harsh conditions of space, but also reflects SpaceX's pragmatic approach to design. The Starship is equipped with Raptor engines, which are known for their high-pressure capacity and efficiency. These engines utilize methane, which can potentially be synthesized from Martian resources, aligning with the long-term sustainability goals of the Mars program. The cost implications of the Starship's reusability are profound. Initially, the cost of a Starship orbital launch is projected to start around $10 million and is expected to decrease to as low as $2 million over time. This dramatic reduction in cost could democratize space travel, allowing a broader range of missions, including those by smaller entities and even individuals. However, the journey of the Starship has not been without its hurdles. The development process has seen its fair share of setbacks, particularly during its test flights. These include several prototypes undergoing rigorous tests, which resulted in explosive failures that provided valuable data to refine the design further. Each test has been a learning opportunity, leading to successive iterations that enhanced the vehicle's safety and functionality. One of the pivotal moments in the Starship's development was the decision to cancel the Red Dragon project. Initially, the Red Dragon was intended to be a cost-effective Mars lander that would use a modified Dragon 2 spacecraft to achieve Mars landings purely through retro-propulsion. However, as the capabilities of the Starship became apparent, SpaceX decided to discontinue the Red Dragon in favor of concentrating on the more versatile and capable Starship. This shift underscored SpaceX's strategic flexibility, opting to funnel resources into a single, more unified architecture that promises not only to facilitate Mars colonization, but also to revolutionize interplanetary travel. In summary, the development of the Starship encapsulates the challenges and triumphs of pioneering space technology. From its innovative design and engineering to the strategic decisions steering its progress, the Starship is poised to be a cornerstone of not just SpaceX's ambitions, but also of the next era of space exploration. As SpaceX continues to refine this monumental technology, the vision of making life multiplanetary inches closer to reality, promising to expand the boundaries of human presence in the cosmos. As SpaceX's Starship development surges forward, the long-term vision for Mars colonization begins to crystallize, encompassing not only the technological feats of interplanetary travel, but also the profound implications of establishing a sustainable human presence on another planet. This vision is anchored in an expansive plan that includes initial cargo missions, the construction of Mars Base Alpha, and an audacious goal of transporting 1 million people to Mars. The initial phase of SpaceX's Mars colonization involves cargo missions, which are crucial for delivering the essential infrastructure needed for sustaining human life. These missions will transport equipment capable of producing vital resources such as water, oxygen, and building materials directly from Martian elements. This strategy hinges on the technology of in-situ resource utilization, which is vital for reducing dependency on Earth and ensuring the viability of a long-term colony. Following the cargo missions, the next step involves the establishment of Mars Base Alpha. This base is envisaged as the first permanent human settlement on Mars, serving as a hub for further exploration and development. It will include habitats, laboratories, and agricultural zones, all designed to support a continuous human presence. The base will not only be a scientific outpost, but also a testbed for the technologies essential for a self-sustaining colony, such as closed-loop life support systems and regenerative environmental control systems. The most ambitious aspect of SpaceX's vision is the goal to send 1 million people to Mars using a fleet of starships. This massive scale of colonization aims to create a self-sufficient society on Mars, complete with its own economy and governance. This plan involves ramping up the number and capacity of Starship flights during each Mars launch window, which occurs approximately every 26 months when Earth and Mars align favorably for interplanetary travel. However, creating a self-sustaining colony on Mars presents not only technological and logistical challenges, but also profound legal and ethical considerations. One of the most contentious issues is the declaration of Mars as a free planet. This concept, promoted by SpaceX, suggests that Mars should be governed by the principles of self-determination and direct democracy by its inhabitants, independent of Earth-based governmental control. This stance raises complex questions about sovereignty, jurisdiction, and the application of international space law, which currently treats celestial bodies somewhat akin to international waters. Moreover, the ethical implications of colonizing a new world are vast and varied, involving considerations of planetary protection, the rights of potential future Martian inhabitants, and the moral responsibilities of altering another planet. These issues necessitate a careful, thoughtful approach, to ensure that Mars colonization is conducted responsibly and equitably. In conclusion, the vision for Mars colonization by SpaceX is a multifaceted endeavor that extends beyond technological achievements to raise fundamental questions about the future of humanity. As this vision moves towards realization, it continues to inspire, provoke debate, and challenge the collective imagination about what is possible in the next chapter of human history. In July 2024, the European Space Agency is poised to advance the frontier of space technology with the launch of the FESAT-2 mission. This significant project will utilize artificial intelligence to enhance Earth observation capabilities from space. With its deployment scheduled on a SpaceX Falcon 9 at Vandenberg Air Force Base in California, FESAT-2 is not just another satellite, it's a pioneering venture aimed at transforming the way we monitor Earth. Equipped with a multispectral camera that images Earth across 7 different spectral bands and integrated with a robust onboard AI computer, FESAT-2 stands out with its capability to process data directly in space. This eliminates the need to send all captured data back to Earth, which traditionally includes images obscured by clouds. The AI-enhanced satellite is specifically designed to ensure that only clear, usable images are transmitted back to our planet. One of the key applications on board FESAT-2, developed by KP Labs, focuses on cloud detection. This technology not only identifies clouds in the images, but classifies them, offering insights into cloud distributions. This feature is crucial, providing flexibility in deciding the usability of captured images. Another groundbreaking application is the SAT-2 map by CGI, which converts satellite imagery into detailed street maps. This capability is particularly beneficial for emergency response teams, enabling them to pinpoint accessible routes during disasters such as floods or earthquakes. This application will be initially demonstrated over Southeast Asia, highlighting its potential to assist in crisis management situations. Additionally, FESAT-2 includes a maritime vessel detection system developed by CEIA. This application employs machine learning techniques to autonomously detect and classify maritime vessels within specified regions. It plays a vital role in enhancing maritime security and supporting environmental conservation efforts by monitoring activities like illegal fishing. Moreover, the satellite incorporates an onboard image compression and reconstruction application developed by GOK. This technology compresses images directly on the satellite, reducing file sizes and thereby increasing the volume and speed of data downloads. Once the images are transmitted to the ground, they are reconstructed with a dedicated decoder. Initial demonstrations of this technology will focus on detecting buildings over Europe. The FESAT-2 mission also plans to expand its capabilities once in orbit by incorporating 2 additional AI applications that won awards in the Orbital AI Challenge organized by ESA's FIFLab. These include an application for detecting anomalies in marine ecosystems and another for wildfire detection, both employing advanced machine learning algorithms. The Marine Anomaly Detection System is poised to identify real-time threats such as oil spills and harmful algae blooms, while the Wildfire Detection System will provide essential information to firefighting teams, including fire location, spread tracking, and hazard identification. With these sophisticated technologies, FESAT-2 is set to unlock a new era of real-time insights from space, significantly enhancing the monitoring and management of Earth's natural and man-made features. This mission not only demonstrates the potential of AI in revolutionizing Earth observation, but also underscores the adaptability of modern satellites to host and operate custom AI applications while in orbit. This adaptability maximizes the satellite's value across a broad spectrum of scientific, commercial, and governmental uses. The onboard AI applications of FESAT-2 are not only innovative, but cater to a range of crucial sectors, enhancing the satellite's utility and impact significantly. Each application is tailored to transform raw data into actionable, timely insights that are vital for various operational and strategic decisions across the globe. Starting with KP Labs' Cloud Detection and Classification System, this AI tool exemplifies how artificial intelligence can refine the process of Earth observation. Traditional satellites often capture and transmit vast amounts of data, including images obscured by clouds, which are not useful for analysis. This AI application smartly identifies and classifies clouds in the images, ensuring that only clear and usable images are sent back to Earth. This enhances the efficiency of data transmission and reduces the bandwidth required for data downlink. The insights provided by this application are crucial for weather forecasting, climate research, and even daily operational decisions in sectors like agriculture and aviation that are heavily dependent on weather conditions. Moving to the SAT-2 map application developed by CGI, this tool takes satellite imagery and converts it into highly detailed street maps. In scenarios such as natural disasters, where quick response is critical, the ability to visualize accessible routes can significantly enhance the effectiveness of emergency response efforts. For instance, during floods or earthquakes, traditional navigation systems might become unreliable if roads are blocked or destroyed. SAT-2 map provides updated and accurate visual data that can help rescue teams navigate effectively, potentially saving lives and optimizing resource deployment. This application's capabilities will be demonstrated initially over Southeast Asia, providing a robust tool for crisis management in a region frequently impacted by natural disasters. The Maritime Vessel Detection System by CIA further extends SAT-2's surveillance capabilities to maritime security. Using advanced machine learning techniques, this application can detect, classify, and monitor maritime vessels in specified regions. This is particularly crucial for combating illegal activities such as unauthorized fishing, smuggling, or violation of maritime borders. By providing real-time data, this application aids in enforcing maritime laws and protecting marine biodiversity, which is vital for maintaining the health of marine ecosystems and the global economy dependent on them. These AI-driven applications onboard FESAT-2 not only demonstrate the satellite's advanced technological capabilities, but also its potential to provide significant real-time benefits across various sectors. The integration of these applications ensures that FESAT-2 can offer more than just Earth observation. It provides strategic insights that can aid in effective crisis management, enhance environmental and maritime monitoring, and support the global response to both human-made and natural disasters. This holistic approach to Earth observation underscores the transformative potential of integrating AI in space technologies, setting a new standard for future missions. The odyssey of space exploration has been marked by a series of groundbreaking milestones that have expanded the frontiers of human knowledge and capability. It all began on October 4, 1957, when the Soviet Union launched the first artificial Earth satellite, Sputnik 1. This marked the beginning of the space age, setting the stage for more ambitious endeavors. Just a few years later, the same nation achieved another colossal milestone by sending the first human, Yuri Gagarin, into space on April 12, 1961, for a one-orbit journey around Earth. The momentum of early space exploration escalated quickly, with the United States marking its own significant achievements. The most notable was the Apollo 11 mission, where astronauts Neil Armstrong and Edwin Buzz Aldrin became the first humans to set foot on the moon on July 20, 1969. This era saw a total of 12 Americans walking on the moon across 6 separate Apollo missions, with the last manned lunar landing occurring in December 1972. Following these lunar missions, the focus of space exploration shifted back to Earth orbit. The subsequent decades were characterized by the development and operation of space stations, which provided platforms for extended human presence in space. The Soviet Union led with a series of space stations, followed by the United States Skylab, and then a fleet of space shuttles that further facilitated low Earth orbit activities. These endeavors culminated in the establishment of the International Space Station, ISS, which since November 2, 2000, has served as a permanent base for humans in space. Construction of the ISS was completed in 2011, and it is expected to continue operations until at least 2024. Parallel to manned missions, robotic explorations have also provided significant insights into the solar system and beyond. Notably, NASA's Sojourner robotic rover landed on Mars on July 4, 1997, marking the beginning of an ongoing era of Mars exploration. Robotic spacecraft have visited all the major planets, landed on the Moon, Venus, Mars, Titan, a comet, and 4 asteroids, and have even flown by Kuiper belt objects and cometary nuclei, including Halley's Comet. The information gathered from these missions has been pivotal in enhancing understanding of the origin and evolution of galaxies, stars, planets, and other cosmic phenomena. Moreover, Earth-orbiting satellites have become indispensable in daily life, providing data for weather forecasting, global telecommunications, resource management, and even national security. As the benefits of space exploration have become evident, the global commitment to space endeavors has broadened significantly. By the early 21st century, over 50 countries had established space agencies or governmental bodies dedicated to space activities. This global expansion includes not only traditional spacefaring nations like the United States and Russia, but also emerging space nations across Europe, Asia, and South America, all contributing to the rich tapestry of international space exploration efforts. Want to visit an interesting exoplanet or dip dangerously close to a black hole? It is not impossible. There's no law of physics that forbids humans from traveling through space, but it's just really, really hard. Here are some potential ways we could travel amongst the stars, ranked from least to most likely. Incredibly unlikely. Faster than light travel. You can never travel faster than the speed of light. At least, that's what we understand through Einstein's special theory of relativity, the revolutionary theory that united space and time can become interchangeable. And while it might be easy to say that a future understanding of physics might do away with that restriction, it could be much harder to put it into practice. Special relativity is one of the most, if not the most, well-tested theories in all of physics. That's because special relativity isn't just a theory, it's a meta-theory. It's a set of instructions that help us build other theories of physics. Special relativity teaches us how space and time are connected in a fundamental way. The nature of this connection puts the speed of light as the ultimate speed limit. It's not just about light or even movement, but about causality itself. Special relativity lays out the fundamental groundwork for the relationship between past, present, and future. In other words, going faster than allows for the possibility of going back in time, which does not appear to be allowed in our universe. Since all other modern physics theories are built on relativity, every time we test one of those theories, we're also testing relativity. While we could be wrong about the fundamental structure of spacetime, the speed limit of light is unlikely to be dethroned anytime soon. Mostly unlikely. Wormholes. Related to the restriction of the speed of light is the seeming impossibility of wormholes. Wormholes are shortcuts in space that connect any 2 points in the universe. These strange objects are a natural prediction of general relativity, Einstein's theory of how the force of gravity arises out of the bends and warps in spacetime. General relativity allows for wormholes by bending spacetime in a very peculiar way. But there's one small caveat. These objects are catastrophically unstable. The moment anything, even a single photon, tries to travel down the throat of the wormhole, it instantly tears itself apart. The only known way to stabilize a wormhole is by introducing a thread of exotic matter. This is matter that has negative mass, which, like time travel, does not appear to be allowed in the universe. It could be that our future descendants discover an alternative way to stabilize wormholes and allow for interstellar travel. But the amount of time it might take to uncover the necessary breakthroughs in physics might be longer than simply going to the stars ourselves. Highly unlikely. Generation ships. If we're stuck without shortcuts or loopholes in physics or other means to achieve FTL travel, then we're going to have to take our time. While sending a spacecraft traveling towards another star is not an issue of physics, it does pose loads of engineering challenges. One fanciful idea to travel among the stars is to build generation ships, large, slow-moving vessels where most of the passengers would never live to see their destination, living generation after generation as a self-contained city vessel that would eventually reach another star. Technically, humanity is already an interstellar species. Years ago, the Voyager 1 spacecraft traveled through the heliopause, the boundary of the solar system, and entered interstellar space. The good news is that it only took a few decades to achieve that feat. The bad news is that it's just getting started. Even at the incredible speed of over 36,000 miles per hour, if Voyager 1 were headed in the direction of Proxima Centauri, our nearest neighbor star at roughly 4.2 light-years away, it would take the spacecraft roughly 40,000 years to reach its destination. That number of years predates the development of the first cities and the advent of agriculture. So a generation ship isn't just a handful of generations, but hundreds of them, all needing to live self-sufficiently in the voids between stars with no additional sources of water, fuel, food, or spare parts. Not impossible, but also highly unlikely. Mildly unlikely. Really, really fast. To get to other stars faster, you can't have a giant lumbering ship. You instead need to be as small as possible. Rockets or other propellants would then get to higher speeds, making the journey as short as possible. Plus, at high speeds, the quirk of relativity helps out. Because of the constancy of the speed of light, movement through space is different than movement through time, and the faster an object advances in space, the slower it moves in time. As it approaches the speed of light, a year for the rest of the universe can shrink to months, days, or even minutes. Unfortunately, these effects only really kick in once an object progresses to more than 90% the speed of light, which is something humanity hasn't come close to achieving. But accelerating particles coming close to the speed of light is something that powerful events in the universe do on the regular, so it's definitely not impossible. But those are tiny particles, not comparatively massive spaceships. Pushing something like a human-sized craft to 90% the speed of light might require more energy than the sun produces in 1,000 years, but that is an engineering problem, not a physics one. Likely, we don't. In the far, far distant future, assuming that our current understanding of physics holds, at least as far as FTL travel and wormholes are concerned, humanity will likely send only a few scant missions to other stars and viable planets. But there's plenty of room here in the solar system, with hundreds of moons and thousands of asteroids to call home. It's a big enough place with plenty of mysteries to uncover. It is home, and there's no place like it.